So earlier we had these little augmented system things, right? And you guys were playing with the matrix button on your calculator. So I'm going to define a 2x2 matrix right now. So a 2x2 matrix, which is going to be a little box that is 2 rows and 2 columns. Rows, columns. You are going to need to remember that it's rows and then columns. It is, I'm sorry, the most obnoxious thing to remember, but you have to remember that it's rows by columns. Okay? So, a 2x2 matrix, that thing, right? You guys see 2 rows, 2 columns? That looks like the left side of an augmented system, right? Okay, that is not a coincidence. This is why. So, a 2x2 matrix is a function from R2 as a vector space to R2 as a vector space. Good with this? You guys remember what a function is and does. Okay. So, here's how it acts. So, I'm going to take a matrix A, B, C, D and multiply by a vector x, y. So this is me doing this function here, which I'll call A, to this vector here, which I'll call x. With me on all this? I am going to say that entire thing is AX. And in your head, for today, well, what the hell? In your head, I want you to put some little parens here and think of this as A of X. You guys with me on that? Okay, so we are taking the function A, we're applying it to the vector X, and that result is going to be pick this vector up, twist it sideways, and drop it on, which you guys have probably seen, done, and heard before. Yes? Okay. So that's going to be the vector AB dotted with the vector XY. You see that? So that's going to be A times X plus B times Y. And the second row is going to be the same thing with the other row. So that's going to be CX plus DY. Yep. So, I tend to, in this class, think of a matrix either as rows or as columns. And you'll see me do one of these kind of things fairly often. You guys with me on that? So notationally, if I'm writing R's with numbers, I mean rows. If I'm writing C's with numbers, I mean columns. So this guy here is row 1 dotted with the vector X and row 2 dotted with the vector X. Is with me on that? So that is one way of thinking about matrix action. Right, which we'll hereafter call matrix multiplication. But I really want you to remember it's a function. Right, it's taking vectors, turning them into different vectors. You guys good with this? Okay. How else could you think of this thing? You guys see that? Like, there's scalar x's here and scalar y's there. Yeah, so I could also think about this as it's like the first column times an x plus the second column times a y. You see that? Those are the same thing. This one we're going to call the column, or this one we'll call the row multiplication picture. That one we'll call the column multiplication picture. We're going to have opportunity to use both of these throughout the semester. Don't pick a favorite. They're like your children. You don't get to pick a favorite. I'm just kidding. If you're in a family with a sibling, you know there's a favorite. Right? So you're gonna pick a favorite, but unfortunately you can't forget the other one. So I really like the column multiplication picture when I'm proving stuff, and I like the row multiplication picture when I'm calculating stuff. That tends to be how I think, but sometimes you need this one when you're proving stuff, and sometimes you want that one when you're calculating stuff. It just happens. Any questions about this idea, a matrix is a function? Okay. The good news for you guys is that I defined this in the 2x2 case, right? The good news is that these pictures hold up in the whatever by whatever case. So if you have a 7x28 matrix, this is still how you multiply. You can either do the row picture or the column picture. Please note, that means something about the input vector. You guys see that? So I'm thinking about A as a 2x2 vector, or sorry, a 2x2 matrix. If I thought about the vector x as a matrix, which I know doesn't make any sense. Yeah, as a just a box of numbers, it has 2 rows and 1 column, right? So I would think about that as a 2x1 vector. Yeah, and then there's this rule that maybe you remember from an algebra class or something. That's the inside numbers have to match, and the outside numbers make this thing's size. So this thing is 2x1 because that's a 2 and that's a 1. Cool? Okay, this should get you started on the first set of homeworks for, in your book. They're on Canvas. Okay. Questions before I shut cameras off?
Can you go from R1 to R2? Like with the normal?
I can circle.
Okay, so can you go from R1 to R2? You mean can you make a function? Is that what you're asking?
In terms of space. Vector space.
Like as a vector space?
So, kind of mismatched dimensionality.
Yeah.
If you're thinking about a function as a transformation from space to space, which is really what we're going to do the rest of the semester. If you go from a space that's smaller to a space that's bigger, there's extra room. So like, I do that all the time when I think about, okay, I live in 3-dimensional space, the floor is 2-dimensional, basically. Just like flat earth with me for a minute. You guys with me on that? Like, 3-dimensional space, that's 2D in 3D. Right, so like, actually, whenever I draw pictures of vectors up here, I'm really embedding the 2-dimensional space that I'm talking about into your 3-dimensional reality by drawing it on the board. You guys with me on that? So that's kind of how the smaller into bigger can work. It's not how it has to work, but it can work that way. And then bigger into smaller is the one that you actually do fairly often.
Really?
Yeah, so can anybody tell me a use case for a 3-dimensional space that you end up only seeing 2 dimensions of?
Draw a cube. Yeah, like project.
Yeah, so my drawings are kind of that reality. There's another use case that's more common. Say that again?
A TV or a screen.
Yeah, anytime you're playing a video game,
Oh yeah.
right?
Huh.
That's a three-dimensional wireframes or whatever the kind of mode of keeping graphics is projected onto a two-dimensional surface. Like, that's why there's money in linear algebra, friends. Because, like, video games are a thing. There's money there. Data science is a thing. There's a frick ton of money there. And that's all linear algebra, all the way to the bottom. So, this is the very first day of kind of, thinking about machine learning. This is also the very first day about just thinking about factors in general. I don't care what you use it for. Probably evil. Machine learning, though, the one caveat, since I just teased this, machine learning deals with huge, huge vectors. Huge, huge matrices. So you're not thinking about your little 2x2 matrix in a machine learning case.
You're 200 times 500 something. It sounds like millions.
I mean, if you're running light stuff, sure. If you're running like image processing, like if you think about the "this person does not exist" website, the matrices in the back end of that thing are a couple thousand by a couple thousand.
Oh yeah.
Like, there's lots of nodes there. We can talk a little bit more about neural network architecture later in the semester. For today, matrices exist. Enjoy them.
Yay.
Okay.
Thanks, Joe.
No.